Welcome to Lesson 10. This will be our last lesson in this constant of proportionality Unit B. And what will follow will be a mid-module assessment. So it's going to assess some of the skills that you've learned in lessons 1 through 10. And that will be your Friday assignment. Will be to take that mid-module assessment and submit that to me so I can take a look at it. Okay? So lesson 10 here is interpreting graphs of proportional relationships. Now, this is the most important part of this lesson today, is this idea of interpreting graphs. Okay? So being able to look at a graph and being able to interpret or being able to decide what is being displayed on that graph. What information can you pull off of that graph? Okay. In the past, we've actually used, and very often you use data to plot coordinate points on a graph, create your graph. Now we're going to look at a graph, and we have done this in the past actually, but we're going to be more deliberate about it. Now this first example, or this first example here, Grandma's special chocolate chip cookie recipe, is more or less a review of previously taught concepts. But we're going to build upon this example as we move through lesson 10. So what I want to challenge you to do right now is to just complete this example here. And if you take a look at what I want you to do here is you're going to use this data, this idea of 4 dozen cookies, 3 cups of flour. Okay, so her special chocolate chip cookie recipe yields, and the recipe itself yields, which means it makes 4 dozen cookies. That calls for 3 cups of flour. Okay, so you're going to use that information to complete this chart, and this is similar to what we did in your snapshot poster, or your poster snapshot submission. Okay, you're going to, right here, you're going to create a table here. In this section, you're going to create a table. Over here, you're just going to answer this question using the table data. Is this number of cookies proportional to the amount of flour? And hopefully you know that answer already, but just want you to explain that there. Come up with a unit rate. Okay. Graph that model. Okay, model that relationship on a graph using your tabular data. And again, does the graph show 2 quantities being proportional to each other? And explain. Remember, there are two prerequisites for that, two criteria. So we should say that would make a graph demonstrating a proportional relationship. Okay. And then go ahead and write an equation that can be used to represent that relationship. All right, so take as much time as you need. You've done this before. Look in your binder in the past and fill this out and come on back and we'll take a look. Okay, so creating a table. Hopefully you create a table similar to mine here. Now, with my table, I decided to use flour as my x variable here, as you can see, in cups, and then cookies I decided to do it by dozen, and that's my y variable. Now you might have chosen to use cookies units, single cookies, therefore this 4 I have here, 4 dozen, would be 48. Now you may have chosen to do that, which may have made it a little bit neater to do than mine. Okay, but let's take a look. So if you did it my way, it would have been 3 cups of flour yielded the 4 dozen cookies. I just chose a few other values. You could have chosen any other values you wanted to. 6 cups of flour or 4 dozen cookies, 12 cups of flour, 16 dozen cookies. Okay. Now, and I was asked here, now this question here about the table here, is the number of cookies proportional to the amount of flour used? And like I said before, when we first started this, I mean, we know it is. Okay, I mean, that answer is yes. because they've set us up. I mean, they already set us up to have a proportion right here. Okay, 4 dozen cookies for 3 cups of flour. All right, so when you have a situation like that, you've already been told more or less that there is a constant of proportionality. Okay, and the idea, if you want to explain this, I mean, for every 3 cups of flour, there are 4 dozen cookies, and that just continues throughout because I, or you, are just creating that. 6 is going to give you 8, and then 12 is going to give you 16 because these are all equivalent or proportional to each other. Okay, and in the simplest terms, this 3 to 4 would be the simplest one. Now the unit rate, okay, over here, the unit rate, what is the unit rate and what is the meaning in the context of the problem? Okay, the unit rate here would be 3 to 4, and again, when we're figuring out our unit rate, we are going to do y, because our k is y over x, and in this case our y is actually 4 and then over our x, which is 3. So 4/3 is our unit rate, or we could say 1 1/3 would also be our unit rate. And what that means is that for every cup of flour, we are able to make 1 1/3 dozens of cookies. Now you see how that's sloppy, and 1/3 is just really awful to work with. Okay, now 1 1/3 dozens is the same as 16 cookies. Okay, so you could have said your unit rate is also 16 cookies or 1 1/3 dozen. So let me write that here. Okay, so unit rate could have been, here, let me just erase all this. You saw what I did there. Unit rate could be written as either 1 1/3 dozens or 16 cookies. Okay, cookies. All right, now when we wanted to graph model the relationship on a graph, again, what I did is, like we've done in the past, is I plotted some points, those easy points, 3 and 4. That's 3, 4. Again, always x, y. Always our x and y axes. Okay, and then we had 6, 8. Parentheses always around those, and then we had 12, 16. Okay, and these are taken directly from my table here. Okay, and I've plotted those points. Okay, and when I do plot those points, I come up with a very familiar looking graph. We've seen this in the past, and the way it looks, it's going to explain the next question. So it asks you, does the graph show the two quantities being proportional to each other? And that answer, of course, is yes, and we knew they were already. But using the graph to tell that is very important. What were those 2 criteria? Okay, first criteria was line goes through origin. Okay, line goes through origin, which it does. You can see right here on the origin always is our 0.00, because if you have 0 cups of flour, you get 0 dozens of cookies. Okay, 0, 0. Line goes to origin, and then line is a straight, all points on a straight line. Okay, and that criteria is also met. Okay, so yes, indeed it is. That graph does indeed show 2 quantities being proportional to each other. So if we were going to go ahead and write an equation for this, we could use D and F for dozens and flour, or we could use our X and our Y as well. So if we said Y equals 4/3 X, can do that. Or it could be y equals 1 1/3 x. We could also round y equals 1.3 x, okay? Rounding that way as well, okay? So any of these equations would have worked. Okay, now example 2 is a little bit different because what they've done now is they're giving you a graph to work with. Okay, and again, I didn't emphasize this before as I should have, but just to always know to label your axes. Okay, so here I have cookies, dozen, flour, and cups, and like I did in mine, which I can't find now, so don't worry about that. But anyway, yeah, so we're back to this. Yeah, so they have a graph here. They're giving you this, the amount of sugar now required to make Grandma's chocolate chip cookies, keeping those cookies as dozens, and sticking with the cups for sugar instead of flour this time. Okay, so now what I want you to do is pause the recording and go ahead and try to do this yourself. And what you're doing now is you're actually doing this interpreting of this graph to answer the following questions. A, you're going to record the coordinates of flour of the points from the graph in the table. You're going to give me the coordinates here. You're going to tell me what do those ordered pairs, what do they represent in terms, and again, all the information you need is right here on this graph. B, you have to solve the problem here. Grandma has 1 remaining cup of sugar, and how many dozen cookies will she be able to make? Okay, so this is going to be a new point on the graph, okay, on the line. You have to plot it above. How many dozen cookies can Grandma make if she has no sugar? Can you graph this on the grid provided above? And what do we call this point? Hopefully everybody is on that already. Okay, so here we go, back to this. Again, pause the recording and interpret away. Okay, so to begin, what I did is I like this process, and hopefully you get into a habit of doing it the same. Is actually creating our table, the table we like and we understand, right next to our graphical representation, which is our coordinate graph that we've been given. So if you did create your table, very similar to the last one, except that our x value now, you can see here, is sugar in cups, and y is still cookies and dozens, and our k, of course, is our unit rate. Okay, so if we did, I just took these points here and just transferred them. And here I am writing, and actually this is the first part here, record the coordinates of the flour of the points from the graph in the table. Sorry, the sugar here. Actually, I think in your binder it says record the coordinates of flour of the points from the graph. And that should be sugar. Okay. Yes, quite a few typos here. But anyway, 4 to 6. Patience is what we need this year. So 8 and 12. And then we had 12 and 18. Well, I forgot one here. Let's see that one. That one is that 24, 16, and 24. 16, 24. It's nice when you create your table with your x and y in the right position. That is easily transferable over to when you create your coordinate points here. Okay, and let's finish this table here. Okay, now these ordered pairs, and actually let me just go to the next slide here. Ask you here, it says, so we've recorded the coordinates of flour of the points from the graph, and actually sugar. Gosh, let me cross this out. Trying to create the sugar. Okay, of the points from the graph in the table. And what do these ordered pairs? What are the values? What do they represent? Okay, so for example, 2 and 3. Okay, so just for an example, just represents 2 cups of sugar or 3 dozen cookies. Okay, 3 dozen cookies. And that's what it represents. Always just bring it back to what it represents. Okay, we always want to know these are not just some silly numbers that are just floating around for us to manipulate, though they are that in some way. But in this case, we're trying to do this in context, that these numbers represent real things. Okay, and again, if we go back here, the same thing here. 4, 6. It represents 4 cups of sugar, 6 dozen cookies, etc., etc. 8, 12, 12, 18, 16, 24. Okay, so they do represent something real. Okay, so now we haven't actually talked about a unit rate. It hasn't actually asked you for a unit rate yet, because you're going to need that unit rate if you're going to do B. So B says Grandma has 1 remaining cup of sugar. How many dozen cookies will she be able to make? Okay, so let's just go back. She has 1 cup. All right, if we're looking here, 1 cup, we need, because what our 1 cup is going to give us, then it's going to give us the unit rate, because remember, our K equals Y over X. And when that X is 1, when this X equals 1 here, okay, we are talking unit rate. Okay, so for every 1 of X, right here, sugar, cup of sugar, we get such and such value of Y. Okay, so we could figure that out this way. If we look at this first one here, 2 and 3, we would have 3 divided by 2. Okay, and that could be our unit rate. For every 3 dozen cookies, you need 2 cups of sugar. Okay, but we could also make that look a different way. We could actually say 1.5 or 1.5. So we would have a unit rate of 1 1/2. And what would that mean if our K was 1 1/2? K equals 1 1/2. Our unit rate. That means we would get 1.5 dozen cookies to every cup of sugar. Every cup of sugar here. Okay, that's what our unit rate is going to mean. So that helps us out a lot. If we were going to go ahead and then plot another point, we would know. And if I can make a little, squeeze a little room in here, make another row on top of this one. Okay. 2, 3. Then we would have 1 cup of sugar. We would have 1.5 dozen cookies. Okay, 1.5 dozen cookies. So that right there answers this question. Grandma has 1 remaining cup of sugar. How many dozen cookies will she be able to make? And that would be 1 1/2. And if we go ahead and plot that point, we could look at 1 cup of sugar. We find that right there, and then 1 1/2. It's about right there. I don't know if you can see. There we go. See, my point is right here, and that does lie exactly on the line, perfectly on the line, which shows that we have done our calculating was correct. Okay. Now this last question, not a trick question. Okay, because it's just going to emphasize one point in particular that we need to consider when we're creating graphs. So how many dozen cookies can Grandma make if she has no sugar? Okay, can you graph this on the grid provided above? What do we call this point? And again, if we look at that point where we have 0, 0 lies right here. 0, 0. Okay, and that point is called the origin, as we know. And because that origin is represented on this line, okay, we know that we have a proportional relationship. Okay, a few interesting things I'd like you to look at concerning this, the graph we just made, is how this idea, or this unit rate, and we figured our unit rate in this problem is 1.5, which again represents 1.5 dozen cookies, or 1.5 dozen cookies for every 1 cup of sugar. Okay, so that's a unit rate because it's based on 1 cup of sugar. That's your unit, and then the rate is 1.5 dozen cookies come from there. And if you notice, every time we make a single unit move along the horizontal axis, along the x-axis here, okay, the independent variable, every time we do that, we move up, vertically we move up 1.5 or 1.5. You can see that first point, 1.5. So then if you continue that, we go to 2, move over 1 horizontally, we move another 1.5 vertically. Okay, so this vertical move, this vertical is our unit rate. Okay, so it's essential that every proportionally written graph includes that point where x equals 1 and y equals the r value, or the unit rate, or also k. We can also say 1k, which is our constant of proportionality. Make it look more like a 1. Okay, so this rate is right here. K is the same. Okay, that unit rate, or that constant of proportionality. So if any graph is going to be proportionally drawn, it'll have to include a point where x is 1 and the y value is the unit rate. Okay, now there are a few exercises that I would like you to complete. Here is exercise 1, and it is a graph that shows the amount of time a person can shower with a certain amount of water. In these times of drought, this is very important. I personally turn the shower off when I am washing my hair, etc. So, and it's good to save water. We can it'd be actually a very fun activity to do this ourselves. Collecting water is a little bit of a difficulty, though. But anyway, this graph shows that that relationship. So I want you to go ahead and look at it, interpret what it is saying to you, and then go ahead and answer those questions that follow. Okay, we have A through F. Okay, and come on back, and we'll check them over. Okay, using our newly found interpreting skills, let's do these questions, A through E here. So A, can you determine by looking at the graph whether the length of the shower is proportional to the number of gallons of water? Explain how you know. If we take a look at the graph, and again our 2 criteria, the origin is actually passed through by the line, and the line is a consistently straight line with all the points existing on that line. So so that answer here would be yes, and that's how I explained it using our 2 criteria. Now answer B, again using this graph to glean information. How long can a person shower with 15 gallons of water and with 60 gallons of water? Okay, so again, we need to take a look. 15 gallons of water, what we would need to do, of course, is to find where 15 lies on the graph. And our gallons rely on our x-axis, or our independent variable. And what we find out, and this is something we don't often look at, we don't look at enough, is in this case, it's not always the case that each point along the x and y axes does actually equal 1. I mean, it can vary, okay, which also varies the way a graph looks. So a lot of times statistics graphs can be used in very mischievous ways, actually. But anyway, in this case, if you notice, from 0 to 20 here, we have 1, 2, 3, 4 points. Okay, there are 4 points. There's 1, 2, 3, 4 points. Okay, so there's 1, 2, 3, 4 segments there. Okay, so each one of those is going to be 5. Okay, because we just take that the amount of that distance from 0 to 20, and we divide it by the 4 segments, and we get 5. So we have 5 actually gallons per segment there. Okay, so that's going to be 5, 10. This is difficult. 15, 20. Okay, so you can see there. So we can find 15, and now we can find 15 once we've actually determined where it lies. So, and again, the question was how long can a person shower with 15 gallons of water? And then if we go ahead and look up from there, we notice that this is a point on the graph, and that's where the gallons equals 15 and the minutes equals 5. Okay, so 5:15. So the answer to that one would be, for 15 gallons, would be 5 minutes. Okay, and then 60 gallons, if we go back and look where 60 is. 60 is nice and neat. We can see it's right there for us. We go to 60 and we go up to go up vertically from there, and we can see that it is at where 60 gallons in 20 minutes. Okay, 60 gallons in 20 minutes. So we would have 20 minutes for 60 gallons of water. Okay. So what are the coordinates of point A? Describe point A in the context of the problem. So let's go ahead and look at the point that they have labeled A, and you can see that point right here. Okay, and the coordinates of A, if we do look down, and again, taking into account that each segment here is 5 gallons. Okay, and we are right there, so we're at 20, 25, 30 is right here. So that's going to be the point where we have 30 gallons of water and 10 minutes. Okay, so point A is 30, 10. So we write the coordinates down, we would write them like this, 30, 10. And in terms of describing that point in the context of the problem, we would just say that 30 gallons of water would equal a 10-minute shower. Okay. Now D, can you use the graph to identify a unit rate? Okay, a unit rate. Well, using the graph to identify a unit rate might not be so easy, but we can try. We can look at some of our points. We know we have 15, 5. We have 30, 10. Okay. We have 60, 20. Okay, these are the ones that we've actually located ourselves. And you might be able to see the relationship here of gallons to minutes. And if we were going to figure out our unit rate or our constant proportionality, you know, K equals Y over X. And if we were to do that, we could just take one like this, for example. So K equals 5 over 15. And we know we can reduce that, again, be sharp with our fractions. We can reduce that to 1 over 3. Okay, so our unit, our rate, our unit rate, or our constant of proportionality is equal to 1/3. And more importantly, what does that mean? Okay, that would mean that for every gallon of water, we could we get 1/3 of a minute shower. Okay, what's a third of a minute? And again, we're looking at this, a third of a minute. We know a minute is 60 seconds. Okay, and we want to split that into 3. Several ways to do this, of course, but we can just see that that would be 20 seconds. Okay, 20 seconds. So 1/3. So our unit rate is 1/3, which again means 1/3 of a minute. Okay, which would be 20 seconds. Okay. So now an E, it says plot the unit rate on the graph. Is the point on the line of this relationship. Again, kind of difficult because we can, what's hard is to find where the 1 is on this graph here. Because as you can see, the 5 is there, so the 1 is going to be somewhere down, let's see, somewhere down here, really close to the 0, 1. And then, yeah, I don't know. That's a difficult question to ask to really figure out in such a graph. Easier when the units are just similar, when they go by 1s instead of by 5s. But anyway, the answer is yes, it is there. We know it's proportional anyway. Okay. Okay. Okay, and that last question there, I'm sorry, there is an F I missed here, but yeah, it asks you to write the equation to represent the relationship between the number of gallons used and the length of a shower. And we've already identified that as y equals 1/3 x. Or you may have used different letters to stand for your different variables. You could have put m for minutes equals 1/3 G, or 1/3 gallons. Okay. Yeah. Alrighty. So let's continue down here. Take a look. Waiting for a screen here. Take a look down here. Oh, here. Okay. Here's example 2. Okay, so exercise 2 here, your friend uses the equation C equals 50p to find the total cost of P people entering the local amusement park. Alright, so C, again, we are given, we've been given our equation, which is C equals 50p. Alright, so if you would go ahead and use that to answer the following questions, starting with creating a table, and then all the way down to sketching a graph and answering a few more questions. Okay, and pause now, finish up, and come back. Okay, so if you made your table, you might look like this. I kept it simple. My P to C, P being my X value when I want to go ahead and eventually graph it, and the C being my Y. Start out with 0 people, 0 money. Okay, 1, 2, and 3 people scenarios. Okay, now is the question B, of course, is the cost of admission proportional to the amount of people entering the amusement park? Of course, is yes. Okay, again, because they've given us the proportion. We started out with a proportional relationship. We know already that it is proportional, but if you want to get more specific or explain a little bit better, we can see all the time for every one person, the cost is 50. 2 people is going to be 100 because that still is 1 to 50, and this is also 1 to 50. Okay. All right, yeah, so we have that. And let's go down here. C, what is the unit rate and what does it represent in the context of the situation? Our unit rate, of course, is 50. And what does it mean? It means that every ticket, every person is cost $50. Okay, so each person costs $50. Or $50 per person. Okay, is our unit rate. All right. Sketch a graph, and if you did that, this would be, if you use this example, it would have been quite easy. Sketch a graph. So again, when it comes time to sketching a graph, that can be a very very particular thing to do, and it sometimes is difficult to make it look reasonable, because now we're looking at values such as one person is $50. Okay, and again, as you notice, I put people here at the bottom, whereas it's the independent variable. I can change the number of people, and cost is on the dependent variable axis because it is dependent on the number of people. Okay, so what I decided to do then, if I'm, in my table, I went up to, let's put this over here again. I lost it before. So my P and my C, remember 0, 1, 2, 3. This was 0, 50, 100, 150. Since I have a cost that goes up to 150, I'm going to need to progress pretty quickly here because I know this is 0. So I'm going to do, I've actually just measured these out already. So I decided I'm going to just use 25 for every 1, 2, 3, 4, 5. So it's like 5 each. That'd be $5 for each line represented, because this should get me to the very top. 125, 150. Okay, and then across the bottom, I'd rather not have the people, each line being a person, because it looks quite silly. So I'm just going to go ahead and make each 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 be one person. Okay, so go like that. And again, depending on how you lay this out, your graph is going to look very, very different. I mean, it's going to be either steeper or it's going to be less steeply drawn. So, like I said before, advertisers, big businesses, they often use statistics and especially graphs to kind of sway people towards what they want them to see. But anyway, let's go ahead and plot this. And if we do plot this for 0, we've got 0, 0. Okay, that's good. We know that's our origin, and pretty good idea. This is going well. We know it's a proportional graph already. So anyway, one person, 50. Here's our 1 and 50. Sorry, I'm having trouble with this right now. A pen, 150. Okay, then we have 2, 100. And then we have 3, 150. Okay, and if we went and drew our line, that's a reasonable line. Okay, there we go. We have our line. We can see that it's proportional. It lays on each point lies on a line, on the line, straight line, and that line goes through the origin. Okay, and again, if we are to ask that question, which points must be on this graph to show a proportional relationship, we would look at the origin, which is 0, 0. Okay, and also the unit rate, which is 50, which is represented right here as 1 and 50. For every unit of X, there are 50 units of Y. Okay, actually E asked that same question I just answered, which what points must be on the graph of the line if the two quantities represented are proportional to each other, and that was, of course, we had talked about 0, 0 as the origin, and then in this case 150, which was the unit rate, where our X value is 1, and in this case our Y value 50. Okay, so it asks you here, would the point 5,250 be on the graph? Now, that is interesting question. What does this point represent in the context of this situation? Okay, so they're asking, would the point that's not 5,000. Excuse me. I thought it was a typo, but no. With a 0.5, comma, 250 be on the graph. Okay, so we need to know. So our relationship 5 and 250, and if we took our unit rate for every one person, $50, we could apply that to 5 and 250, and we can see that it is indeed proportional because 1 times 5 is 5, and then 50 times 5 is 250, so we have a proportional relationship here. So yes, indeed, it would be on our graph. Okay, so let's go ahead and summarize our lesson here before you move on to your problem set and exit ticket. So here's our lesson summary. The points 0, 0, and 1 are, where R is the unit rate. Okay, and we just talked about that last problem. Will always fall on the line representing two quantities that are proportional to each other. The unit rate R in the point 1 R represents the amount of vertical increase for every horizontal increase of 1 unit on the graph. And remember, when we went over 1 horizontally, we would go up by the unit rate. Okay, in in that one case it was 1.5, and just in this last case with the costs and the people at the amusement park, it would have been actually 50. Okay, so for every movement over 1 in that last amusement park case, the R would have been represented by 50 units or $50. Okay. The point 0, 0 indicates that when there is 0 amount of one quantity, there will also be 0 amount of the second quantity. Okay. These 2 points may not always be given as part of the set of data for a given real world or mathematical situation, but they will always fall on the line that passes through the given data point. So you may be given some data, but you won't necessarily be given the point 0, 0, and you won't be given the point 1 R. Okay, but those points can be plotted. They will, if you plotted them, they will fall on that straight line. Okay, so this is the end of lesson 10. Go ahead and finish your problem set and your exit ticket. The next quote-unquote lesson is actually going to be a mid-module assessment. All right, and we'll just go through the instructions in lesson. Well, it won't be a lesson. It'll just be mid-module assessment, and then I'll have you submit that to me. So look forward to that next. Okay.